Hello everyone, welcome to this video. In this video, we'll be looking at a result which states the order of an alternating group. So, the order of an alternating group an, where n is greater than 1, that is given by n factorial by 2. We saw one example where this thing was justified, right? Now we will prove this result in general for all alternating groups. So in order to do that, because we know the order of the group Sn is n factorial, we have to prove that the order of alternating group is exactly half of this order, right? So the order of an, that is exactly n factorial divided by 2. So what we will do here, we will prove that because we know the elements of an, they are all the even permutations. So therefore we will prove that the even number of even permutations, that is equal to the number of odd permutations, right? So this is what we will prove here. The number of even permutations is equal to the number of odd permutations, because if that is done, because when they are in total, they form the elements of Sn, and we know the order of Sn in n factorial, and if both of them they are equal to each other, so then it would just be the half of n factorial, right? So this is the point here. So for the proof, we see that if we consider one odd permutation, say alpha, right? If alpha is an odd permutation, then if you multiply that, if you multiply this alpha by some other transposition, so that means previously it was written as odd number of decomposition. Suppose alpha was written as 3 decomposition, so it was an odd permutation. Now if we multiply it to one other permutation, so now it will become 4, right, in this case. So therefore it would definitely become an even permutation. So the transposition 1 2 multiplied with the transposition alpha, right, this permutation alpha, that is an even permutation. And also this is one thing, right? So now for a particular alpha, we are saying for a particular odd number here, if we take another another permutation beta which is not equal to alpha, then the result that the transposition 1 2 composed with alpha, this thing is not equal to the transposition 1 2 composed with beta. They are not equal to each other, right, according to the cancellation property. Now this thing would cancel with this thing, so we are left with alpha not equal to beta. So that means if we have two different permutations, they are not equal to each other. So if alpha beta, they are not equal to each other, where both alpha and beta are odd, so that means this transposition 1 2 composed with alpha, this is even. This is also not equal to this even, right? So this is what we are saying. So from here we can make out that at least there are at least as many even permutations as there are odd ones. So that means even permutations are less than equal to the odd permutations. So this is what we are saying according to this rule, because this even permutations, they depend on this odd permutation here, right? In a similar manner, as we have considered the permutation alpha as an odd permutation, now we may select alpha as an even permutation, right? Next we may select alpha as an even permutation. So for each even permutation alpha, the permutation where, so suppose alpha is an even permutation, so it is written as product of two compositions. So in this case, if you multiply it by one more transposition, say 1 2, so it will definitely have odd number of transpositions here, right? So what does that mean? It would mean here that in this case, the transposition 1 2 composed with alpha, that is not equal to the composition of the transposition 1 2 with beta, whenever both alpha and beta, they are not equal to each other. In this case, this alpha and beta, they are even. Whenever the even permutations, they are not equal to each other, the odd permutations are also not equal to each other. So therefore in this case, the number of odd permutations are less than equal to the number of even permutations. So the number of odd permutations, they are less than equal to the number of even permutations. And previously we saw that the number of even permutations, they are less than equal to the number of odd permutations, correct? So combining this equation and this result here, we have the number of even permutations and odd permutations as equal. And because we know alternating group consists of all the even number of permutations, so they would exactly form half of the total permutations which are the member of Sn. And we know the order of Sn is n factorial, so therefore the order of this an is n factorial by 2. And this is what we wanted to prove here in this result. So I hope you understood this result well. Well, that is it for this video. Thank you for watching.